For this lesson, we're going to be working through applications of vertex form. So we're going to be doing a few word problems that are going to focus on our vertex form equation as well as graphing. So before we get started, we're going to do a quick review of vertex form. So our general equation of vertex form is y equals a x minus h all squared plus k. And just as a reminder, this h represents the x of our vertex with our sign switched. And then our k here represents the y of our vertex. So that is an important thing to remember as we move forward because we will be using that a lot throughout these questions. So our first example here, some boaters use a red flare in an emergency. The flight of the flare is modeled by the function h equals -9 t minus 3 all squared plus 83, where h is the height in meters of the flare and t is the time in seconds that the flare is in flight. The first thing we want to do is we want to sketch a path of the flare. So this is just going to be a sketch. It's not going to be perfect, but it will help to give us a little bit of an idea of how our flare is moving. So again, it's just a sketch, so we can use it just as a guideline, but it definitely won't be perfect for us to use to make conclusions from. So the first thing I want to do in order to figure out what my scales should be and what my graph is going to look like is I want to start by identifying the vertex. So from above, using my h and k, I know that my h, with the sign switched, is the x part of my vertex. So in this case, we will have 3. And then we know that k is the y part of my vertex. So we know that we have 383. So I'm going to make a scale where I know I could see 383. So I'm going to start by putting the scale on my y-axis, or my h in this case. And I'm going to go up by 5s and just write on every other one, but you can choose a different scale if you prefer. And then I'm going to label that with height in meters. So although it's a sketch and it's not going to be super accurate, we do want to follow all of our graphing rules and have our titles on all of our axes. Next, we're going to put a scale on my x-axis, or in this case represented by t. And that bottom axis is representing our time in seconds. And I'm going to go up by 0.5 and just write on every other one, but it's up to you. As long as you pick something that makes sense, that's all that really matters. So now let's start sketching our graph. We know our vertex is at 383, so we're going to do our best to put a point at 383. It's not going to be perfect, but it'll help give us an idea. So I go to 3 on my x-axis, and I'm going up to 83, which should be about here. And when I'm doing a sketch, I often like to write out what my coordinates are on the sketch, just because it's not going to be perfectly accurate, so it does help you to visualize your graph a little bit more. Next, let's figure out where it's going to cross below. So we know that we have a little boat somewhere over here, and we don't know exactly where it goes, but we do know it's going to go from our little boat, so something like this, and hit at 0. And then we also know that parabolas are symmetrical. So if it shoots right from 0, 0, looking at my graph, I'm going to put down my axis of symmetry just to keep it symmetrical and help me to identify how it looks on the other side. And now I'm going to try to mirror that line on the other side. So if I mirror that line on the other side, it should go through 6 over here. Something along these lines. And again, it's just a sketch. I'm not using my step pattern, so I don't have a ton of accuracy here. Now that we have a sketch and a little bit of a visual, we can use this to start answering some questions. So the first thing is what is the maximum height reached by the flare? So if I look at my graph, my flare goes up, reaches its maximum height, and then it turns around and starts going towards the ground. So the maximum height reached by the flare is 83 meters. Next, we're trying to find out when does that happen. So again, let's follow our flight path of our flare. At 0, it starts, it's going, it's going, it's going. And then at 3 seconds, it hits that max height, turns around, and starts going down. So at 3 seconds is when we hit our max height. Okay, now we want to see what is the height of the flare after 2 seconds. Now, it is challenging to use our graph at this point just because it is a sketch and it is not very accurate. If we go through and do this and yours ends up being accurate, that's amazing, but I would encourage you not to bank on that. So what we're going to do is we're going to do this algebraically. So what is the height after 2 seconds? So seconds is a time value. So we're just going to sub in t equals 2 into our equation. So wherever I saw a t, I'm just going to write a 2. And now we're just going to follow our rules of BEDMAS to simplify. So we have to deal with the stuff in the brackets first. Next, our exponents. Then we're going to deal with our multiplication. And finally, we're going to do the addition and subtraction. And we will get 74. So therefore, at 2 seconds, the flare is at 74 meters. So if I look on my graph over here at 2 seconds, I'm a little bit below 74. So what probably happened is I should have drawn my parabola wider. So it is a little bit hard to see there. So that is exactly why we do this algebraically. Okay, so next what we want to do is we want to find another time that the flare is at a height in part D. So we want to find another time when it is at 74 meters. So what we're going to do is we're going to set H to 74 meters because we're trying to find the times when it's at 74 meters. And if I look here, it's a little inaccurate. Actually, maybe I'll just make my graph a little bit wider to represent where it's really supposed to be. There we go, that's a little bit better. So at 2 seconds, it's at 74 meters. And sometimes when you're drawing sketches, it really does make a difference how you draw it. So sometimes you do have to fix your graph if you realize you drew it a little off. So at 74, I found there's one at 2 here, but it also reaches 74 again over here. So what we need to do is we need to figure out when that happens. So let's do it algebraically. We're going to sub in h equals 74. So that will give us 74 equals -9 t minus 3 all squared plus 83. And now we're just going to do opposite operations. So let's move that 83 over. So that will give us -9 equals -9 t minus 3 all squared. Next, we'll divide out that -9 on both sides. And we'll get 1 equals t minus 3 all squared. Next, we're going to square root both sides. And one thing that we have to do here is we have to remember that we're going to have a plus minus 1 here. And this part is probably going to confuse so many people, so bear with me for a moment. The reason I have a plus minus here is because negative 1 squared is 1 and 1 squared is 1. This step always happens, and we've actually used it before, we just didn't write this out. So anytime we square root a number, we actually have two answers. And typically, we've only ever really done this with Pythagorean theorem, which we would ignore the negatives anyways. But here, we can't do that. So if I square root a number, I always get plus minus. And again, that's because positive 1 squared equals 1, but negative 1 squared also equals 1. So this here actually gives us two different equations. So we'll have 1 equals t minus 3 and negative 1 equals t minus 3. So if we solve for t, we'll have 1 plus 3 equals t, and negative 1 plus 3 equals t, which will give us 4 equals t, and 2 equals t. So we already had 2, right? We already had 2, which was right here, but now we found the second one, which was right here. So we can say, therefore, the flare is at 74 meters at 2 seconds and at 4 seconds. And this also makes sense because of the fact that my parabola is symmetrical. So that is another way we can do it as well without doing this complicated algebra. Next, we're going to find our y-intercept. So what we're going to do is our y-intercept happens along this line here. So we're trying to find out when it hits that pink line. So to find a y-intercept, we're going to sub in x equals 0. Or in this case, we're going to sub in t equals 0. So we have h equals negative 9, 0 minus 3 all squared plus 83. First, we deal with the brackets, then our exponents, so what we've learned is our y-intercept is actually right here at 2. So what does that mean? This is just a sketch. So again, it's not super accurate, but if I look here, it actually goes at 2. So what we've learned is here's my little boat, and it shoots off from 2 meters and then continues up. So what we've learned is therefore the boat is 2 meters tall, or it's shot from a height of 2 meters. That's how high it is at time equals 0, right when we start. Now, we want to find another point on the graph using point F. So again, just like before, we could go through and we could do all of that algebra, but I wanted to take a moment to work with the symmetry of it. So similar to how we could have used symmetry before, if I come over here and go here, at 0, it was at 2. So it's likely that using symmetry, that at 6, it's also around 2. So our graph was fairly accurate, but definitely could have required some changes. So that's why we make a little sketch just to give us an idea, but we can't guarantee it. So doing things algebraically is always a good idea. And then once we've done some things algebraically, then we can really start to use the graph more because we understand where everything is. Okay, so that was a bit of a challenge question. We're going to break this down a little bit more and do some questions that are a little more straightforward. So the first one is at a fireworks display, a firework is launched from a height of 2 meters above the ground and reaches a maximum height of 40 meters at a horizontal distance of 10 meters. The first thing we want to do is we want to determine the equation to model the flight path of the firework. So there's a few different things we're being given here. And I'm going to draw a quick little sketch just because I find that that's the best way to understand what we're looking at. So we're told that we have our horizontal distance down here, and we have our vertical distance up here. And our little firework, there's a little guy here, and he shoots off a firework from here at 2 meters high. So at time equals 0, when a stopwatch begins, he's standing at 2 meters high, and my little firework goes here, it explodes, how pretty, and then it continues down to the ground. The other thing that we're told is that it reaches a maximum height of 40 meters. So we know that up here, we reach a maximum height of 40 meters, and that happens at 10 meters horizontally. So now we know that our vertex is at 1040, and then this little point over here that we're given is 0, 2. So now from last lesson, hopefully this is seeming familiar, we're being given the vertex, and we're being given a point. Our goal is to fill in our equation, so we're looking for y equals a, x minus h all squared plus k. So let's start by filling in our vertex. And now we need to solve for a. So if I wanted to solve for a right now, I have way too many variables. So I need to start by plugging in my point for x and y. Now I'm going to simplify those brackets. Sorry, I'm running out of room. I'm just going to have to move over here. Now I'll do those exponents. And now I can solve for a. So let's move that 40 over. And we'll divide that 100 out. So we'll have negative 0.38 equals a. So what we've learned is therefore the equation is y equals negative 0.38 x minus 10 all squared plus 40. Now, the firework continues to travel an additional 1 meter horizontally after it reaches its maximum height before it explodes. When does it explode? So we know that its maximum height happens at 10. So we're looking for the part that happens at 11. So we're going to sub in x equals 11. So we have y equals negative 0.38, 11 minus 10 all squared plus 40. And that means that it is 39.62 meters high when it explodes. And finally, we want to figure out how long does the firework travel above the height in part B. So we found that point here at 11 meters. And we also need to find it over here. So we want to figure out what that time is above that line. So similar to before, we need to figure out when else it hits 11. So we can do it two ways. We can do it using the symmetry of this, or we can do it using algebra. So we're going to do it using the symmetry. So we know that symmetrical right around 10. So if that's 11, it has to be 9 on the other side, so 10 is in the middle. So for 2 seconds, it's above that. So using the symmetry of the graph is a really good idea. So once I know where my vertex is, if I know one point on the other side, I can just find the matching point on the other side, and I know that that is the other point that's at the same height. So there's a few practice ones below. Give them a try, and then take a look at the full solutions of them below.